Okay, today we're going to go over periodic properties, chapter 7. Okay, um, so everything today is going to relate to the periodic table in terms of going to the right, going to the left, and going up and going down. All right, uh, the first thing I'm going to talk about is what determines the size of an atom. Okay, so the size of the atom is determined by the cloud, the electron cloud. So if I consider that, what causes that cloud to get either bigger or smaller is the amount of protons in the nucleus. Now, as the electrons add in shells, every time you complete a shell, you have an equal amount of protons as the number of electrons in a shell. And they tend to have an effect where they cancel each other out. So the first property that really comes up I'm going to talk about is Z effective. And Z effective is your effective nuclear charge. Now, at any one point, when you start off with like neon, a noble gas, okay, inside it, I have an equal number of protons and an equal number of electrons, okay? They effectively cancel them out. So as I start building on my next level, I go to sodium. Sodium has one electron, which effectively is held in place by the one extra proton. So the Z effective would be +1. Magnesium has two electrons held in place by that second proton, so its Z effective is a +2. And right across the board you go +3, +4, +5, +6, +7, and +8. Okay, there's a formula for Z effective, but that's pretty simple. So what you're looking at is, if you're looking at 8 valence, 8 outer electrons, alkalis are held in place by one extra proton, alkali earth are 2, 3, 4, 5, 6, 7, 8. As you tend to go to the right, your Z effective increases. And in a given group, your Z effective is constant. Okay, so that's the first trend. Now, the formula for Z effective is officially Z minus S. Z is equal to your atomic number, and S is equal to your shielding electrons. Now, what the shielding electrons are is they're that inner completed shell of electrons that every noble gas has. So as I look at the shielding, anything below helium is shielded by 2. Neon is shielded, anything below neon is shielded by 10 electrons. Anything below argon is shielded by 18. And we're going to talk about that. That's known as the shielding effect. And if I look at Z effective just in calculations, like I said, it's very easy just to look at the trends and say 1, 2, 3, 4, 5, 6, 7, 8. But if I look at something like magnesium, magnesium has 12 electrons, and I would subtract the inner core, which is the noble gas, minus 10. So I calculate it to be a +2. If I did the same thing for calcium, 20 minus 18, +2. Okay, so I can go anywhere on here. Aluminum is 13 minus 10. Is a +3. And that, for metals, that ends up being their usual charge for the main group elements. Now, I'm not really going to consider transition metals right now. It's just going to increase the level of complexity. I will say this, well, maybe I should show you. If I try to do anything below a transition metal, so if I try and do tin, or selenium, sorry. Selenium has 34 protons, so its atomic number is 34. Now it's just not a matter of subtracting out the 18 from argon. When you cross the transition metals, remember, these aren't outer electrons, these are inner level. So you have to add these, always you have to add the 10 extra electrons to the 18 from argon. So it's minus 28, which ends up being a plus 6. Now, that doesn't mean that the oxygen family has a plus 6 charge. It means its Z effective is a plus 6. It means those electrons in its outer shell are held together by 6 extra protons. If I try and do a transition metal itself, okay, you have to, like if I did vanadium, which is a 23, I would subtract out the 18 for argon, but I got to include the 1, 2, 3 that are in its shell. So that would be minus 21, and I get a plus 2. For most of the transition metals, except the exceptional configurations, you get a plus 2, because what you're really losing is your 2s electrons. Okay? So if I tried zinc, zinc would be 30. Now I have to take the 10 electrons that are in the inner shell and add them to the 18. So it's minus 28. So it's a plus 2. And that's the effective. Okay. Now I made this little chart for you, which I'll do. And I know it's at the bottom, but I would say the most important trend to know, and I made this up for you guys to know your periodic trends. Z effective increases as you go to the right. And if I was to label Z effective on here, if I was doing a test, I would just go ahead and label it plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7, and plus 8. And I was mentioning the transition metals in terms of Z effective, but up and down, as you go down, Z effective is a constant. Okay? And that's because left and right, you always have the same number of shielding electrons. So even though I haven't mentioned it yet, shielding effect left and right is constant. You always have the same number of shielding electrons. That's your noble gas. So you can kind of figure this stuff out when you're doing configurations, that your shielding electrons are the noble gas itself. They're the core electrons. Up and down, shielding effect, as you go down, well, you go from 2 to 10 to 18 to 36. So shielding effect as you go down increases. Effectively what that does is that cancels out your Z effective and keep the Z effective constant as it increases. I said I would do one exceptional. If I try and do copper, copper's configuration is argon, and the exceptional configuration is 4s1, 3d10. So its atomic number is 29, that's its Z. And the inner core electron, the outer electrons are 18 plus these 10, so 28, and you get a plus 1. So for Z effective for copper, silver, and gold, it's all a plus 1. If I do it for chromium and molybdenum, chromium or molybdenum, let's do molybdenum just to be different. I got 42, and then the inner core is the 36 argon. So molybdenum is argon with a 5s1 and a 3d10, and effectively it's taken that outer core electron and made it become a shielding electron in the middle. So molybdenum is going to be 42 minus 36 plus 10. So that'll be, oh, it's not, I'm adding all 10. To do molybdenum, you would just add the 1, 2, 3, 4. Sorry, it's not 3d10, it's 3d5. I would add those 5 electrons to the 36 shielding electrons. That ends up being 41. And again, you get a +1. So all the exceptional ones have a +1 Z effective. Alright, dog. 2. Shielding effect. You consider that to be S. Okay. And shielding effect is the shielding of your outer valence electrons by the inner core electrons. Okay. We said on the pattern, shielding effect is constant left and right, but increases down. It's the Z in the equation. It's the S in the equation for Z effective. The exceptional configurations, because you are bringing in an outer electron, the S, into the inner core. So in all your exceptions, your shielding effect increases. That effectively allows the remaining S electron to become more easily excited. So when we see that in their physical properties, gold, silver, and copper are all very conductive because that outer S electron is held loosely. Okay, so they all tend to be conductive, and they all tend to be very lustrous because now this one has an easier way of you don't need to put as much energy to ionize it to make it increase, to excite it. Because they excite easily, they're all very lustrous. And that's the effect that you get with copper, silver, and gold. They have a beautiful luster because of their loosely held S1 electron. Same reason for chromium and molybdenum. Chrome is very shiny because it has a 4s1 electron that's highly shielded. So it makes it conductive and shiny. And so we've covered 2 of our periodic properties, shielding effect and Z effective. And now, after that, most everything in periodic properties comes, you have to consider number 1, Z effective, number 2, size. Okay, size becomes the second most important, and then shielding effect, which affects your Z effective. So all 3 of these things are the base. So let's talk about size. Okay, if I look at a periodic table in the beginning of the year and I ask students, well, we're adding protons and electrons, and I ask them what happens to size. People think because you're adding protons and you're adding electrons that it's going to get bigger. Well, that is false. When you go to the right, you get smaller. As you going up and down, go back to this. Okay, go back to what I said in the very beginning. As you go to the right, as you get more protons in the middle, the electrons in the cloud shrink because of the attractive force, because of the Z effective. So the Z effective makes the size go down. So that's why we want to know about Z effective. So the most important thing to know is the size of the atom decreases as you go across the period. As you go down, you're filling shells. Okay, that's your energy levels. And since electrons occur in shells that increase, as you go down, the size increases. So going down, size increases. Okay. And now what this all comes down to is, what happens with atoms and them losing and gaining electrons. And we have a term for losing electrons, we have a term for gaining electrons. Um, let's see. And I gave you this nice little sheet, and this nice little sheet is for you to define uh, all your characteristics. Now, ionization energy is the energy required to lose an electron. Okay. Um, Atoms do not give away electrons, although I've heard a lot of teachers make that statement. It's a terrible statement to make. Uh, Electrons are held in place to atoms by protons. And it's not that they give them away, it's that some have a low ionization energy. So as we draw an equation, if I have them, usually they're metals. And if I add energy to that metal, like I'm going to draw it like a thermochemical equation, then the metal will give up its first electron, okay, and become a +1. So usually metals are characterized by low ionization energy. They don't give them away. These are metals. It's that their valence electrons are easily taken away, not that they give them away. Okay? An example of this would be like group 1 alkali metals, which might be like sodium becoming a +1. Now, what's leaving are the valence. The outer electrons are the ones that are easily taken away because they're far away from the nucleus and they're highly shielded. Okay? If I do a second one, I give it more energy, more delta H. I take the metal, which already has now lost 1, okay, and it becomes a metal with a +2, and it loses another electron. That's called your second ionization energy, and that might be an example, calcium, +2. Okay, if I put in more energy, plus a metal with already has lost 2, now it becomes a +3 metal, +1 electron. And that would be aluminum. Now, I've got some nice sheets to show you. This is in your textbook and this is in your PowerPoint, and this is successive ionization energies. And if I looked at sodium, which is helium, with not helium, neon, with a 3s1, magnesium would be neon with a 3s2, aluminum would be neon with a 3s2 and a 2p1, and so forth. These are your inner core electrons. These are your valence electrons. These are the ones that are easily lost. Here's what this sheet shows you. That for sodium, to take away that first electron is a very low energy. So these electrons on this side are your valence electrons. The outer. You have a very low ionization energy to take 1 electron for sodium. And then for magnesium you get low, low, that means 2 of them can leave. And then the third one, it comes from the inner core. Suddenly in the inner core, if I calculate a Z effective for that, for aluminum, it has 13 protons. Well, once I strip away the 2 outers, the inner core becomes helium. So the effective Z effective of aluminum with a plus charge becomes a +11. If I do it for magnesium, it's 12 minus 2, a +10. If I do it for sodium, now these are with charges as ions, it becomes 11 minus 2, it becomes a +9. So these actually would be less likely to lose an electron than a noble gas, which is a +8 Z effective. So your Z effective can go higher if you've already lost your outer electrons. So if I'm looking at something like sodium, you have a 1s2, 2s2, 2p6. That's its effective. And then your outer core is your 3s1. If I was to take away that 3s1, I'm really talking about what's holding the inner core in place, this one. And what's holding it in place is you have 13 protons, and then the only thing that's shielding this one is the 2 from helium. So I'm pretending that this one's already gone, its valence is gone. I'm saying, okay, what's the Z effective of that one right there, the next one? Well, what happens is your energy to take that one goes way away because it's now close to the nucleus and its Z effective has jumped up massively. When I take away the valence electrons, that's when you get a big jump. With the +3, it's the first is low, second low, third low. That's your big jump. That's why aluminum has a +3, and so forth, if you just go on. Now, when you get into the non-metals, they're very much not likely to not form positive ions because successively you have to dump a ton of energy in to get them to ionize. Okay, but it is possible to ionize the first electron, but not so likely. All right, that's what this chart's about. Okay, electron affinity. First of all, let's talk about ionization energies trend. Okay, as you go to the right, two things are going on. The size is decreasing, and the Z effective is increasing. Now, if I look at the force on that electron, I go right back to Coulomb's law. The electrical force equals, I think I better stop this video right here because it's going to cut out on me if it hasn't already. I get a 24-minute limit. I just kind of discovered that.